There is an American scientist, but you know, America, the United States, East Europe, some pioneers coming there. So Pipkin worked at Brown University in a moment when many German Jewish scientists moved to the United States. Pipkin, around 1970, started to study materials in which you have nearly inextensible fibers. And these are the main structural elements in nowadays most advanced airplanes. And he didn't manage to understand some details, important details of the mechanics of these materials. But he wrote many papers, and he had beautiful ideas with which we are fighting now. If you want to understand what a body which is constituted by very resistant fibers to elongation, which however can bend with a low deformation energy, with a low bending energy, you must change completely your way of reasoning, but you still are introducing a set of Lagrange, finite set of Lagrange parameters. You are still writing action in terms of these parameters. You change Cauchy first gradient conceptual frame, but you are always inside the Lagrangian frame. And this Pipkin understood very well, and for this reason he was isolated from a cultural point of view. He was the dominating group, believed that everything was inside. Look in Cauchy models. Look, this is a standard situation. You should not believe that Galileo was considered dangerous or was considered heretic for religious reasons. That was a fight between two groups of scientists. Okay? Jesuits were not a group of religious people believing in stupid things. They were very clever scientists. Jesuits were the group of full professors of the church. Okay? And they had some deep concept, deep knowledge, and some blocked conceptual frame. Okay? And Copernicus, Kepler, Galileo were out of the cultural paradigm in which Jesuits were limiting themselves. So it was not a question of believing in the Bible or not. This was a war between ideas, mathematical models of reality. Okay? Pipkin was excommunicated by Truth. A very typical, of course, Truth couldn't burn Pipkin. You know that Giordano Bruno was burned because of his conceptual. So, what I'm trying to teach you is a frame which up to now has been general enough to include every mathematical model for physical phenomena. Of course, never believe that this is the most general one. You must be open to another one. Nobody knows what you will need. Okay? So I'm stressing the differences and the wars, intellectual wars between different, there is a German philosopher of science, his name is Kuhn. He's talking about intellectual scientific paradigm. Somebody is inside an intellectual paradigm and he moves inside it. Everybody is in a paradigm. The difference between somebody who is clever and somebody who is not too much clever is simply this one. The clever people knows he's inside the paradigm. The more stupid people believe that his own paradigm is the only way possible for thinking. Okay? So, you can model this fiber reinforcement body with many kinematical descriptions. Okay? However, once you have introduced the most suitable finite element scheme, you reduce it to a Lagrangian system with a finite number of kinematic parameters. I don't try to tell you how fiber reinforced materials can be modeled because we could need another 30 hours. But once you have reduced the action of your original system using finite elements, you are back to a Lagrange having Q1, Qn, Q dot 1, Q dot n as a Lagrange function by means of which you can construct the action function. Okay? This n could be, for instance, 10 to the 4th. So you could have many degrees of freedom. Okay? So you must learn how to deal with functions of many variables. There was a stupid colleague of mine who came to me one day and he told me, why n? 3 is enough. Because you have a material particle and you need 3 parameters for describing this material particle. So R3 is good, Rn is too general. So how can you explain to such a person that when you have a continuous body, you can cut it into small pieces, you can partition it into small pieces, and you can attribute to each of these pieces 10 degrees of freedom, and then if you have 1,000 of these small pieces, then your system has 10 to the 4th degrees of freedom. When you use console, you have a window, and you choose how fine, refined is the grid. When you choose one given refinement level, you choose N. Are you aware of this? So if you use coarse, you have a given N. If you use fine, you have another N. If you use very fine, you have another N, bigger. Okay? Now, every Lagrangian system is governed by the equation. By the way, a true Lagrangian person writes Lagrange equation with the minus here. Okay? You can distinguish a true Lagrangian person in this way. Because fake Lagrangian, fake mechanicians multiply this equation times -1 and change the sign. But in this way, they prove that they forgot that you get this integrating by parts. Okay? So if you want to send a signal, write the equations with mind. This is I don't know exactly, I'm not aware of Polish history as I would like, but I'm sure that in Poland we had many historical periods when groups of politicians were secretly meeting for fighting against the power active in that moment. Could be, I don't know, Solidarność group in a given moment. Okay. In Italy, we had patriots fighting against Austria. Okay? And they sent each other signals. Okay? Send a signal to everybody and write equations with a minus there. This will declare that you belong to the group of variation of people. Okay? How many equations you have written here? You have to understand the power of this notation. Here, I is 1, 2, n. So you have written 10 to the 4th equation in your blackboard with this notation. So, how can you believe that such a powerful notation is painless? If you want to write 10 to the 4th equations, you must spend your life in writing all of them, right? This is very painful. So how you can believe that this pain can be reduced without costs? To reduce your pain, you must understand a new notation. You have to master a new conceptual tool. Index notation. Okay? Now, I will teach how to linearize these equations. You have to understand the title of today's lecture is Linearization of Lagrange equations. Okay. Linearization of many equations. Galileo linearized one equation, the equation of pendulum. You can find the linearization of pendulum in every book of physics. Okay? And yesterday I told you how to do. this linearization with words, but you have to do this linearization with all calculations if you want to proceed and generalize it. Okay? Now, why we are interested in linear equations? We are interested in linear equations because there are beautiful theorems teaching us how to build the solution. How to build. The building of the solution is easier if you have a linear equation. So it is not true that reality is influencing mathematical modeling so as it is practical to study linear systems, we study linear systems. It is the other way around. We are building only systems which undergo small deformations because we can study only these systems. So it is our mathematical capability which is influencing reality, not the other way. It's not true that reality is allowing us to limit ourselves to linearized equations. It is our limited capability of studying equations, in particular, our capability of studying only linear equations, which is obliging us to build systems undergoing limited small deformations. Now, with computers, we can do better. So, what happens is that we are studying non-linear systems, and we are building non-linear systems. Okay? Good. So, we assume to have found an equilibrium configuration. So we have assumed, as we did the calculation yesterday, I'll give you again only the result. We assume to have found a solution of this family of equations, which we can call equilibrium conditions for our Lagrangian system. Okay? So, we have found that Q0, never forget, this is Q01, Q02, Q03, Q0n. This means a vector made of n components. Okay? So you need n equations if you want to find it. Okay? Of course, these equations in general are not linear. Okay? So, if you have a linear system of equations, you have a matrix, you have the unknown vector Q0. This is equal to a given B. This is a linear system. This system already has one solution. One solution means one vector being the solution. It could have infinite solution. It could have no solution. It depends on the matrix A and on the vector B. The study of this equation is due to a French who didn't prove all results, and an Italian who was professor in Napoli, Capelli, Rouchet Capelli. We are talking about the theorem of ruscettamenti. If you have that the rank of A is equal to the rank of the complete matrix AB, then the system has a solution. Okay? Then if the number of unknowns is equal to the rank, to this common rank, then you can reduce this system into a square system, that is A has exactly n rows and n columns, and you can solve this equation, because in that case the matrix A has an inverse matrix. Its determinant is different from 0, so you have depth A different from 0. Otherwise you could not have that the rank of A is maximum and it is equal to the number of unknowns, and therefore you can easily solve this problem multiplying everything times the inverse. This which I have written for you here is so-called Cramer formula for solving linear systems. However, you can have infinite solution for a linear system if the rank of A is smaller than the number of unknowns. So if it is smaller than the number n. Okay? So already in the very simple case of linear systems, please revise these things, or if you need, ask me where to study these things, because without these concepts you are dead. CONSOL is solving every instant many thousands of linear equations of this kind. So you have to understand exactly what it is doing, and you cannot understand if you don't master these concepts of linear algebra. But what I want to tell you is that already in the case of linear algebra, you have no solution sometimes, one solution in other situations, infinite solutions in other situations. So if you ask to your computer to try to solve a problem which has no solutions, it will become crazy. If you ask your computer to calculate a solution when there are infinite solutions, it also may become crazy, because you cannot choose which one you want. So you must always ask good questions to your computer. So you must characterize the unique solution which you like, and you must ask him to look an approximation of this unique solution. Okay? Now, if you have linear systems, you have a theorem. This theorem was proven in the middle of 19th century. So you know how to direct your code. if the equation is not linear, you are in trouble. You can have more complicated situations. What can happen? I hope that when you were a student in high school, somebody spoke to you about this equation. Second order equation. You know, nowadays the majority of engineers with a master's degree have serious troubles in finding the solution of this equation. The equation has been studied by Greeks, so it is not clear who understood. Let us use mathematical analysis, so we go quick. We are quick. If A is positive, then when x becomes minus infinity or plus infinity, this becomes dominant and you get a positive value. What you get is something like that. This is the graph of this equation. But you can have three different possibilities. Either this is crossing in 2 points y0 axis, or it is tangent to y0 axis, or it can be this way. So, depending on what is doing the discriminant of this equation, so if this animal is greater than 0, you have two solutions. If this animal is equal to 0, you have only one solution. If this is negative, you have no real solution. Okay? So you understand that when this set of equations is non-linear, the possibilities are much more complicated. You can have no solution, many finite solutions. You can have infinite solutions. So non-linear problems are much more complicated than linear problems. And there is no general theorem telling you how to solve a non-linear system of equations. There are tricks for characterizing particular classes of equations and how to find in an approximate way the solutions of these non-linear equations. But the situation is dramatically more complicated. Much more. Okay? So, following the idea of Galileo, it was decided to linearize that equation when the motion is close to an equilibrium configuration. So, what we do? We assume to have a motion q of t, which is like this: q0 plus a small number epsilon times q tilde of t. So you have a small perturbation of this idea is already, I know that you cannot speak Italian, so you cannot appreciate the wonderful way of writing of Galileo. Galileo writing has been used in high schools not for teaching to students science, but for teaching to students Italian. The Italian of Galileo is of an outstanding elegance. It is clear, it is very well taught, very elegant. Now, when he writes about equilibrium, stable positions, is using the example of a particle moving along a guide. So think about a metallic wire and a small material particle. You can think about a plastic, small piece of plastic with a hole in between, and it is following the guide in this way. So I still remember when we read this in high school. If you take the material particle here and you give a small velocity to this particle, starting from this equilibrium configuration, what will be the destiny of this particle? It will fall down here. It will arrive at the same level here with zero kinetic energy. Imagine that you worked this guide very well, so you have no important friction for a long time in. Okay? This can be done. Then you arrive here, it stops. Then it falls down and it comes back here. Then goes to the other side and it reaches this level. So you can have a very large disturbance. If this is your Q node, of course this is a one-dimensional Lagrangian system. So you have only 1 degree of freedom in this example. But if something can happen with 1 degree of freedom, it will happen in much worse and complicated ways if you have 10 to the 4 degrees of freedom, right? So you must be clever in imagining what could happen to the unstable systems made of 10 to the 4th degrees of freedom. Okay? If this can happen with 1 degree of freedom. So, Galileo understood that these equilibrium conditions are dangerous. If you are here instead, a minimum of potential energy, then you move a little bit. You give to your particle a small velocity. This particle will remain in the neighborhood of your equilibrium position. So this tentative solution you can write. So you can find a Q tilde of time, which multiplies a small parameter x plus Q0 gives you the motion of your system. So we limit ourselves to the study of a particular class of motions. The motions which are close to an equilibrium stable configuration. Because this is called equilibrium stable configuration, and this is equilibrium unstable configuration. precise. Maybe for sure I will come to Warsaw, and if you will decide to follow my lectures also there, I will complete these lectures. So the idea could be I add details to what I'm telling you. So what I could do, for instance, is to tell you what a French scientist, French German, Dirichlet. Actually, I never understood. I should discover better the story of Dirichlet and a Russian scientist, Lyapunov. They studied in great detail what happens, how to classify equilibrium configurations into stable and unstable. So how to discover which are stable configurations. Okay? And then to prove in a rigorous way that motions close to stable configurations have a structure like this. Lyapunov did a lot. Now we assume that this is true and this is small. Okay? So we are studying small motions in the neighborhood of an equilibrium stable configuration for our Lagrangian system. Okay? What do we need to do? We know that this is true because Q0 is an equilibrium condition. So I take dl over dqi, the partial derivative of the Lagrangian function with respect to qi, and I write it, by the way, this is a function of q and q dot. Okay? In general, this function is complicated. Okay? Then we can decide to write a Taylor expansion in the neighborhood of the motion qt equal q0. So the idea is to write this using a Taylor expansion and truncating this Taylor expansion at the first order. In this way, this equation of n plus n variables, which is very complicated, will become an equation of linear equation of 2n variables. So instead of having a very nonlinear, in general, very complicated equation, we try to reduce not equation, function. We try to reduce this function into a linear function. Okay? Why? Because we assume that Q0 plus the motion Qt is given by Q0 plus a small number epsilon times Qt del of t. And Qt del of t is smaller than 1. So this animal is smaller than epsilon. there is nothing tragic or too new for you. If I have one function of one variable, I can choose x0 and I can find Taylor expansion, and I can say that close to x0 my very complicated function can be approximated by a linear function. How do we find the linear function for one function of one real variable independent and one real variable dependent? We write f of x is equal to f of x0 plus f prime of x0 times x minus x0 plus infinitesimal. Okay? Now, our problem is that here we have an animal in which you have n plus n variables. So you have n functions, the L over dqi, I is 1, 2, n, and these n functions depend on 2n variables. This is the difficulty. But from a conceptual point of view, we are handling a Taylor expansion truncated at the first order, forgetting a linear approximation of this. Now, when this linear approximation will be valid, when Q is close to Q0 and when Q dot is close to 0. So when we have a motion close to the particular motion equilibrium. Okay? And as Q dot of t is equal to 0 plus epsilon q tilde dot of t, the Taylor expansion which we are trying now, this Taylor expansion will be valid when epsilon is suitably small. Okay? So from the, if you consider the technical point of view, there is no difficulty except the need of writing a Taylor expansion for a function of n variables. Okay? We already did this. For this reason, I slowly calculated for you some derivatives last time. So I try to write here dl over dqi q dot equal dl over dqi q0 0 plus, now I must generalize this. We said it many times. This is the derivative with respect to qj. Remark, qi, I is blocked. Now J is varying. I cannot call this index with the same name as I, exactly for the same reason for which I cannot use a for command with I, and inside another for command having the same name index of the other for command. Okay? It's very strange. M&MoCS understood this, and then computer scientists understood that the for command needs different indices, and I'm using for you the reverse of them. I'm teaching you the rules of M&MoCS indices, exploiting your knowledge about for commands. Okay? But the trick works. So this J is different. So I write dl over dqj, dl qi. This element is calculated in q0, 0. And here I write qj minus qjz. So what I'm doing? I'm calculating d over dq1. Okay? Calculating this partial derivative in the equilibrium configuration, and I'm using the small perturbation of q here. Then I have d over dq2, and I'm writing q2 minus q2z, and I'm doing this n times. So I'm using the generalization of this formula, where I have the derivative with respect to the first variable, derivative with respect to the second variable, the derivative with respect to the nth. So I'm using the Taylor expansion formula for functions of n variables. Okay, and instead of writing 10 to the 4th addend, I'm using this clever trick. So, my dear friends, I cannot do in another way. If somebody asks me, write it more simply, I cannot. Because I cannot write for you 10 to the 4th addends. Okay?
Is there any relation between J and I?
I is the number you have fixed at the beginning when you wrote one of these n equations. So I can be everything between 1 of n. Okay? J is all n's, is spanning all n's. J is 1, 2, 3, 4, up to n. So there is no relationship between I and J. Understand this carefully. dl over dqi depends on all q1, q2, qn. Okay? This function depends on all q's. So when you write this Taylor expansion, you must estimate how this quantity is varying if you vary q1, how this quantity varies if you vary q2, how this quantity varies if you vary qn. When you have a function of n variables, you are telling that your dependent variable depends on many variables. And here you are estimating how dl over dqi depends on each independent variable. And each independent variable can do what it wants. And you must control each of variation. This is the power of mathematical analysis. It gives you the tool for controlling complex dependence. Okay? Understood? Go and read your book of mathematical analysis with a different eye now. Okay? Don't believe that this animal is theoretical. I told you the story of Angela Merkel deciding if to abandon Greece or not. Okay? The independent variables in economy are so many that experts in economy could not decide the final result of chasing Greece out of Europe. So they couldn't write the correct function on the correct number of variables to forecast the final output of a given decision. Why? Because N in economy is usually very high. So they cannot control, up to now, the consequence of a decision. Okay? It is not ended. You need dl d over dq dot j. This is another form independent of the previous one, so I can use the same index. Okay? Because you are summing here and you get a result. Here you have another form before dl over dqi calculated in q0, and here you have q dot j, because q dot j0 is 0. The not perturbed motion is equilibrium. Okay? Plus infinitesimals. Okay, keep in mind these equations, which we will need, but I need to erase them now. By the way, when you're using console, the command normal modes for getting eigenvectors, eigenvalues, console is doing this calculation. So I'm giving you the recipe used by console for finding those beautiful modes you have seen for the complex structures. So now, of course, we have plus infinitesimals. Here you have epsilon squared. So you can decide, I want to kill these infinitesimals because epsilon is small. Okay? Now, look, I'm talking very slowly. So if you don't understand, tell me. It is crucial that you understand what we are doing in all details. You must become master of these things. Okay? Otherwise, Tommy will not invite me anymore. This is very bad. Tommy is a good boy. I want to make him happy. Okay? So, this quantity is 0 plus a linear function of q Qj minus Qj naught. And another linear function times Q dot. Okay? So, dl over dqi calculated in q dot. This is the animal which we need here in this Lagrange equation. This is equal to 0 plus you know how you have here a qj, qi. So you have a number with two indices. Do you know how practical expert engineers are calling this? They are calling it the rigidity matrix. So what is astonishing? If you call it rigidity matrix, you are practical. If you call it Hessian matrix or Lagrangian, you are a twisted mathematician. So if you try to understand, you are twisted. If you learn by heart things without understanding, you are practical. And I have a mental disorder. I cannot teach. I cannot use something which I never understood. I cannot understand. Okay? I believe it is very unhealthy that we are teaching to students using slides. You must be able to give your talk at the blackboard. You risk to say something which is wrong. I did it sometimes. You think it at night, and the day after you go and you say, sorry, I was wrong. Okay? This matrix, now this is a matrix. It's not a function anymore because you are estimating it in Q0, 0. Okay? So we call it capital A 0 ij with two indices. Then here you have qj minus qj0. We call it epsilon q tilde j. Okay? Then you have another derivative, another matrix. Okay? This matrix, usually practical engineers say it is 0. Indeed, it is 0 sometimes. However, if you want to study gyroscopes, you know, the spinning top. Do you know that nowadays, airplanes are using spinning tops for finding their direction? So this is a practical term. Okay? This animal is called gyroscopic matrix. It came out the first time when studying gyroscopic effect. Okay? So, let us call it friendly, G0, Ij, epsilon, Q tilde dot J. Okay? Okay? It can happen that this G0 is 0 or negligible. But there is no reason for not writing it. We try to be as general as possible. You know, Shakespeare was copying probably a Greek source when said that bigger reality would be always more complicated than your philosophy. So, when developing a model, when you can, for free, being more general, do it. I mean, here, there is nothing, you can kill this term, okay? Why? Do you have a reason? Is it simpler? You still have to do a Taylor expansion. Saving one matrix is not worth. Okay? Okay. So now we can write this in a matrix form. So if you call dl over dq the vector made with n components, dl over dq1, dl over dq2, dl over dqn, this is equal, nearly equal, because you are neglecting infinitesimals higher order. This is equal to A0 epsilon q tilde plus G0 epsilon q tilde dot. Wonderful. We have linearized one part of Lagrange equation. Okay? We must work a little bit with this term now. We have linearized this animal. Okay? We must linearize this animal here. So the calculations we have done yesterday, we use again. Okay? Remember, yesterday I have calculated something which we used now for Taylor expansion. Okay? So this derivative, d over dt, dl over dqi is equal, you know what? I write this formula and then we have a coffee break. Okay? I have to pull in your head slowly this. By the way, I want to tell you this. I have learned this subject when I was 21 years old. I never needed to revise it. It is maybe now the 24th time that I'm teaching this in class. And I never revised it. Why? Things which I have studied later, I need the notes in my hands for giving it. Don't waste your moment. What you are learning now, it will be forever. Don't believe I will do it later. Your brain will remain blind if you don't build your it in the correct way now. Okay? It will be a loss forever. If you don't teach to to a child to use a language between 0 and 9 years, he will never learn how to talk. Actually 7, but there are some cases in which they manage to force somebody to learn how to talk when he was 8 or early 9. Okay? To learn this mathematics, either you learn it now or you learn it never anymore in your life. Okay? So painfully we calculate this derivative, we go to have a coffee, and then we attack the linearization of this element. Okay? So this is d over d2j of dl over d2i times qj dot and then you have plus d over dq dot j dl over dqi q double dot j, and I don't know if I forgot this or not yesterday. If I did, I apologize. Of course, you have the partial derivative with respect to time. You have d over dt of dl over dq dot. Okay. Of course, I forgot the dot. Also yesterday I forgot this dot somewhere. Okay? Because we are trying to attack this element. Okay? So this is the sum over j, sum over j. Okay? Okay. You have a function f of x. Okay? Then you have a function g of x. Then you have f of x equal fx0 plus f prime x0 xl plus. So you have a Taylor expansion of f. And you have a Taylor expansion of g. And you ask yourself, what happens to the Taylor expansion of the product of f and g? Okay? This I need, so I will try not to erase this. Okay? So, this is f0, fx0, g, x0. Then you have epsilon this plus epsilon that. I don't know if you are rediscovering Leibniz rule. So you have plus, which is the factor epsilon, this times that. Okay? And then you have epsilon, this times that. Okay? So you have epsilon, f prime x0 0 G X 0 plus G prime X 0 plus F X 0 plus infinitesimal of higher order. Okay? One. What we are doing, we are rediscovering Leibniz rule. Okay. Now, why I wanted to tell you this, which I hope you already know, you have already seen. Because now, my experience is that students become a little bit upset because I do the calculations quickly and they feel bad. This angle is epsilon q tilde dot j. You agree? Because q dot starts with the first order. Okay? So this animal cannot have zero order. Zero order term in Taylor expansion is this animal. Okay? If one of the two series has 0 plus first order, here you have 0. So the product starts with the first order. You agree? So this animal here has epsilon solid, and here I can have only the 0 order of this animal. Okay? This friend we already met, because I hope that you have proven the Schwarz theorem for commutativity of partial derivatives. Anyway, this animal is this is a matrix. We have to calculate it in Q0, 0, because otherwise we get higher order terms. So now I am writing this in this way. I have the correct equation, and now on the right hand side I'm neglecting every term of higher order with respect to epsilon. Okay? So if I write this Taylor expansion adding other terms, I will get epsilon squared. Okay? If this animal, this is 0 plus epsilon something plus epsilon squared something else. But if I write this with epsilon here times epsilon here becomes epsilon squared, and I can't make it. So this first factor appears at first order in our expansion only with the value constant estimated in Q0. So notwithstanding the calculation, your phases are absolute. Here I'm looking for the first term of my expansion. Okay? But F0 is 0. So this term is not appealing. So what I get? I get epsilon F prime times G calculated in X. So this animal is epsilon times this annual calculated in x0. And I have no other terms. Okay? So this first addend we can call equal G bar in Q0, 0, which is this matrix, Q dot. Okay? So G, I, J, Q dot. The same reasoning applies here. You have epsilon Q tilde double dot J and this annual is times something. If I want the term epsilon, I have no other chances than considering this in Q0, 0. So I can write this plus mass. This is called, by practical people, mass matrix, or matrix of masses. So this is Mij calculated in Q0, 0 times, here I have epsilon Q tilde double J. Okay? Okay, we can do similar calculations, but let us assume that the Lagrangian is independent of time. So this anymore we can treat it exactly in the same way as the others. Okay. So I repeat slowly this answer. Your phrases seems a little bit worried.
And M was mass matrix, yes?
Yeah. So, where is the technical difficulty we are facing now? The technical difficulty is this one. I have one function, and I know the Taylor expansion of this function, and I have another function, and I know the Taylor expansion of this second function. So I write these expansions. Of course, I didn't want to write either of the terms, which I decided already I want to neglect. Okay, I want to find my expression with small epsilon, and I want to consider only linear terms in epsilon, the small parameter. So I write f of x equal fx0 plus epsilon f prime plus other terms. Similarly, g. And I got this, which is trivial. Okay? You agree with it? Now, what we have here? We have something starting with epsilon. So you have no zero order. Okay? And I want to consider the Taylor expansion of this product, truncating it at the first order. So everything which is higher in epsilon, epsilon square, epsilon cube, everything, I don't want to write. So I write here nearly equal. Okay? Good. So I take this expansion and I write the particular case of one of the two factors starting with 0. What I get? 0 order term is 0, because 0 times everything is equal to 0. The second order term, I have this addend is 0 times G prime. Okay? So what I am left? Epsilon F primes times G calculated in X. I have nothing else at the first order. Okay? So what I have to do? I consider this first factor calculated in unperturbed motion, Q0, 0, times epsilon Q tilde dot. This animal here is first order. You have no 0 order. So in order to get the first order approximation, the first order Taylor expansion term of your product, you simply need to take this quantity and you need to calculate it in Q0, 0. So the equilibrium configuration of Q0 with the velocity 0. We call it G bar, Ij, this is a matrix, epsilon Q dot tilde J. Similar reasoning is here, because the acceleration you get deriving 2 times. So you have epsilon, second derivative of Q tilde. This is exactly the same structure as the other one. So finally, I can write here that d over dt minus dl over dqi is nearly equal to what? G bar ij epsilon q tilde dot j plus mij epsilon q double dot q tilde double dot j.
What about the last derivative?
The last derivative, okay. If Lagrangian is independent of time, it is easy. Exercise. Find this term with the Taylor expansion. You will introduce 2 more matrices. The same, because you have dl over dq I. You can expand dl over dq dot in Taylor series expansion. Okay? So you have a term epsilon q tilde and the term epsilon q dot tilde. Okay? So write it. I don't know why I forget systematically these things. So you will get 2 more matrices. Maybe we can check. Tomorrow you try to do the calculations painfully. Do them. If you manage to do them, good. Okay. If you don't manage, good, we do them together. But trying will allow you to understand better. Okay? Of course, if a Lagrangian is independent of time, this element is 0. Okay? So you have two more matrices. You will see there is no difference in what we are doing next. Okay? So, good idea. You try to do the expansion following all what I said you up to now. There is nothing different. Okay? You have to do what we did for the L over dqi. For the L over dq dot I, you have to do for d over dt of dl dq dot. Okay? So it is a Taylor expansion of another function, which is slightly different, but the structure is the same. Okay? Good. Now, in a matrix notation, we get that d over dt, dl over dq dot is equal to g bar epsilon q tilde dot plus m epsilon q tilde double dot. Okay? This is the matrix notation. So I am writing the same thing as a matrix. This vector is equal to this matrix, product row times columns of this vector, plus this matrix, row times columns, this vector. This is an equivalent way for writing these two things. Okay? You remember, if I have a matrix, I must take this row, this column, I have to do this times this times this, and so on. What do I get? I is the column, the row, J is the column index, and this is GI1 Q dot 1, GI2 Q dot 2, and so on. This is row times column product. So two different notations for the same animal. Okay? And I wrote it here already. I hope you are familiar with this row times column notation, which is a trick used sometimes for avoiding summation over repeated indices, but it is equivalent. Now we have all ingredients for writing this set of equations. Okay.
So here in G bar was yes.
The summation is over J. The beauty of Levi-Civita notation is that you can call it as you like. I must be very careful when I do row times columns, because I must tell you which is the row and which is the column. Okay? This is an appropriate observation. The beauty of Levi-Civita notation is that when you define, this J here is the derivative with respect to Qj. So there is no ambiguity. I can write the index as I like. Because I'm telling you what it means. The derivative with respect to Qj of the derivative with respect to Q dot I. So wherever I place the index, it is not important. But if I write it with a matrix notation, I must tell you which is the index of the column, which is the index of the rows. The bad news is that one half of the book writes the index of the column first and the index of the row after, and the other half vice versa. Okay? Okay, so I erase this because we have copied it up, and I write Euler-Lagrange equations for our Lagrangian system in matrix notation. So dl over dq is equal to A0 epsilon q tilde plus G0 epsilon q tilde dot. Then I have minus d over dt dl over dq dot, which we wrote as minus G bar epsilon q tilde dot plus epsilon n q tilde double dot equal 0. So I simply copied minus. I simply copied the equation. I mean, this is the general equation. I have linearized, of course, I should write here plus higher order infinitesimal. Okay? The zero order version, the first order truncation of Lagrange equations is given by this, which I wrote here. Okay? Epsilon simplified. I can call this difference G. Okay? Look what we get. M Q tilde double dot equal to G Q tilde dot plus A0 Q tilde. This is the most general equation for the small motion in the neighborhood of an equilibrium stable position.
But the G is here.
G is G0 minus G bar. Okay? Because you have Q dot on both.
And G0 is gyroscopic matrix.
G0 is one gyroscopic matrix. G bar is another gyroscopic matrix. And G is the two complete gyroscopic matrices. Of course, inside here you can have also dissipation. It is a question of names, actually. Now consider this animal, this equation, in a particular case. N equal 1. Then you have N x double dot equal G x dot plus A Q x. Of course, we have to carefully check the sign of this equation. Okay, we didn't worry about discovering which is the sign of G, which is the sign of A, because we were developing a Taylor expansion. But you recognize that this is the equation of something we have already studied. This is the equation of harmonic motion with this equation. I gave you some calculation to do. Now, what we discover is that this is not a very particular case. This is a very general case. Because if you accept the idea to have a mass matrix n times n, a generalized gyroscopic matrix G, and a rigidity matrix A0, okay? You have a slight generalization of this animal in matrix notation, and this slightly more general equation is governing every motion in the neighborhood of every equilibrium stable configuration. I have got this equation, this one, without any assumption except one, except two. The system is Lagrangian, and the motion is close to an equilibrium stable configuration. This means that if I am clever enough to solve this linear system, then I can solve the motion of every system in the neighborhood of an equilibrium stable configuration. Do you have a building? Do you have an airplane? Do you have a device whatsoever? If your equations are Lagrangian, if you can find an equilibrium stable configuration, and if your motion is close to the equilibrium stable configuration, then the equation of motion are these. So when Ivan has shown you the vibration modes of a structure in the eigenanalysis, frequency analysis for a structure, Consol was solving this system of equation for the structure you were considering. How? Introducing finite elements, finding the finite dimensional Lagrangian, as I told you, then calculating the Taylor expansions as I have shown you. Okay. Now the presentation proceeds in a certain way, which requires your knowledge of the concept of eigenvalue and eigenvector of a given matrix. Okay? So you know what we do. We sketch this part, then we will decide what we will do next. We could stop here, so we have something to complete in future, or you can study this subject in a good book. You cannot survive any dynamical analysis without knowing what eigenvalues and eigenvectors are. Okay? I want to tell you that this system can be terrible. I mean, this matrix M, if you have a discrete finite element integration scheme with 1 million degrees of freedom, this M is a matrix 1 million rows, 1 million columns. This G is similar, this A is similar. So you cannot conceive to do anything calculating by hands. However, the general theory of Fouché-Capelli and the general theorems talking about diagonalization of matrices are valid. So you can teach to your computer how to find the solutions of this equation. And it finds this. And you see in the screen of console, or whatever is your program. This is the miracle of all this theory. So I cannot give you an example. If I write a 4 times 4 matrix, of course, you can do something. You can try to do some calculations, but you don't get any idea of what your computer is doing. You must deal with the most general theory. Okay? Now, for talking a little bit about the general theory, let us start by assuming that G is equal to C. So we find the most general situation without gyroscopic terms and without distribution. Just to have an idea of what we are doing. So the equation becomes M Q double dot. I will soon be tired and I will not write tilde anymore. Okay? Equal A, also the 0 will drop. Q tilde. Okay? So, problem. Can I find the solution of this system of equation? The answer is, in general, yes. There are beautiful theorems which are showing you how to find the solution of this system. Now, let us try to remember something. The matrix M is equal dl over d Mij is dl over dq dot I dq dot j. calculated in Q0, 0. So this is a symmetric matrix because you have the partial derivatives with respect to the same variables q dot I, q dot j. Okay? So this is a symmetric matrix. The matrix of masses is symmetric. Okay? Now we assume that this matrix is definite positive. Why? Usually, you remember, I wanted to do the procedure in the most general case because I want to show you that this procedure is valid for a generic Lagrangian. Of course, you can have some difficulties. Imagine that one row of this M is 0. Then the rank of M is not maximum. So this equation could not give you all second derivatives. So we need to do some assumptions about these matrices. Okay? In general, the Lagrangian is kinetic energy minus potential energy for mechanical systems obeying Hamilton principle. And an important class of mechanical systems have U, which is independent of Q dot. So U does not depend on velocity, Lagrangian velocity. This is a particular case. Your structure, the one you have seen, those you have seen with console, obey this particular assumption, are following, verifying this assumption. So, the Lagrangian of a mechanical system of the kind you have seen with console, the Lagrangian is kinetic energy minus potential energy, and the potential energy depends only on Q. It does not depend on Q dot. And the kinetic energy is a quadratic function of velocities. Okay. But what we have done is more general and can be applied in more general situations. Okay, so you don't have the Hamilton straitjacket. So you can try to attack a problem where the Lagrangian is not a kinetic energy minus a potential energy with a kinetic energy quadratic function of Lagrangian velocities. Okay? In the particular case we are talking about, M is a definite positive matrix. What about A? A is Aij is dl over dqi dqj. Calculated in Q0, 0. Remember this 0. Okay. So this is equal to the kinetic energy Q dot I, Q dot J, Q0, 0, minus the second derivative of U with respect to Qi, Qj. I not calculated well the distance, so I rewrite this. Now, this animal, if t is quadratic in Q dot, okay, you calculate the derivative with respect to Q, it remains a quadratic function in Q dot. Okay? This is mathematical analysis, simple, but imagine to have this. You have a quadratic function in one variable, and the coefficient depends on the other variable. You calculate this, the derivative with respect to x. What you get? dA over dx y squared. Okay? So you get a quadratic function in terms of y. You have changed the coefficient. Okay? So if t is a quadratic function of Q dot, and you calculate the derivative with respect to Qi, Qj, you have a quadratic function in Q dot with a different coefficient. Okay? I give you an exercise, so you try to understand better. Write the kinetic energy T and use the standard notation which you have in analytical mechanics. T is equal to A H K function of Q, Q dot H, Q dot K. This is a standard quadratic form. If I calculate dt over dqi, this is equal to dA over dqi, q dot. Okay? So, the derivative of t with respect to qi is another quadratic form. And this quadratic form has as coefficients the derivatives of the first quadratic form, the old one. Okay? Now, if you calculate this element for Q dot equals 0, you get 0. So, this element is 0 for Hamiltonian systems, so for systems having Lagrange equal kinetic energy minus potential energy. I don't know, maybe one day, working with Tomek, you will discover that a biological system is not Lagrangian. Sorry, it's not Hamiltonian. It is will not be Hamiltonian. Its Lagrangian will be kinetic energy minus, will not be kinetic energy minus potential. Why? Because you will have a new biological energy playing a role in your phenomenon. You have growth of a tissue, and this growth needs another structure of Lagrange equations. So, you will be very careful. You will go back to this equation with your general Lagrangian, and you will not use the particular form I am calculating for you. Okay? So, in the particular case we are studying now, Aij is minus the Hessian derivative of potential energy. When potential energy has a minimum, you have a stable configuration. So, capital A is a definite negative matrix because the Hessian matrix of U is definitely positive. So, introducing the Hessian matrix of U with a minus sign here, you can see this is symmetric because this matrix is symmetric. Okay? So you have M definite positive, H definite positive. Both of them are symmetric, and you need to solve this equation. This is what console is doing for you. Okay, before stopping, I want to tell you how we attack this problem. Using a lot of linear algebra, nowadays useless for engineers. Okay? M is definite positive. Therefore, you have an inverse of M. So you can calculate. Maybe you understand now why to have a good software, you need a software calculating quickly the inverse of a matrix. You know, console is a tool calculating quickly inverse of matrices. Telling it quickly. In one word, inverse. Okay? So, you multiply everything times M minus 1. So you get Q double dot equal M minus 1 minus H Q. You have minus a matrix, I call it B, Q. Now I can tell you how I started my exam of analytical mechanics many years ago, just as a preliminary question for being allowed to continue my exam, my laboratory. They asked me to find the conditions for which this B has a basis of eigenvectors. So the question is, I give you a matrix B. Do you know when this matrix has a basis of eigenvectors? This is a topic of linear algebra. Now, you should have studied this. Okay? You must study this again. I will not try to tell you anything about the mathematics of this problem. What I want to try now is to tell you why this problem is so important. So I give you some ideas which should motivate you to study carefully the problem of eigenvalues and eigenvectors of a matrix. I tell you the following. If I know an eigenvector and an eigenvalue of a matrix B, then I can find a solution of this equation. Okay? I tell you more. If I know that B has a basis of eigenvectors, I can give you all solutions of this problem. So, if you know how to find a basis of eigenvalues and eigenvectors of a given matrix, then you can solve this ordinary differential equation. If you can solve this ordinary differential equation, you can solve all small motions of every Lagrangian system. So eigenvalues and eigenvectors nowadays are one of the most important concepts in applied engineering. Now, I try to show you why what I'm telling you is true. What is an eigenvector? This is a real number. This is eigenvalue. This is eigenvector. The eigenvector is relative to an eigenvalue. An eigenvector is a vector which verifies this nice property. B, the matrix B, applied to U is equal to a real number times U. So the action of the matrix B on the vector U is equivalent to multiply U times a real number. So eigenvectors are well behaving. You take a very complicated matrix, you calculate B, this matrix, on U, and the final result is U times a number. It is a dream. Okay? The good news is that this dream happens. It happens enough times that you can use this dream for solving this equation. This is the good news. Okay? if I have found an eigenvector, I wake up and I try to check if this animal is a solution of this equation. Okay? So what I do? This is a number. This is time. This is a vector. So Q double dot is equal to what? U, which is not dependent on time, times alpha squared in alpha t. I calculate the derivative of this animal. The first one is alpha e alpha t. The second derivative is alpha squared e alpha t. Okay? Then I have here equal b. No, sorry, I don't write equal. This is q double. Then I try to calculate bq. Okay, bq is equal. B is linear. Therefore, E alpha t comes out. So I have E alpha t, B of U. Okay? But B of U, as you have chosen so carefully U, that it is an eigenvector, this is equal to lambda times U. E alpha t. Now I try to verify the equality. Okay? So I try to find alpha to have the equality. So I write U alpha squared E alpha t equal minus lambda U E alpha t. Okay? Now, this cancels. U times alpha squared is equal to minus lambda U if and only if alpha squared equal to minus lambda. Of course, to have this equality, U has to be different from 0. So now you understand why in the definition of eigenvector, you say an eigenvector is a vector different from 0, which verifies this equality. So what I have discovered? I have discovered the beautiful property that if I have an eigenvector, I find a solution of this equation. Which solution? This one. So, if I have a matrix, I find one eigenvector and the corresponding eigenvalue, then I have a solution of this equation.